In this second video, we're going to look at the natural phenomena that influence our global climate. This is our big concept, is that there are natural phenomena that can and do affect our global climate. Some of the arguments presented against climate change are that these natural phenomena are naturally causing this climate change. So we're going to look at each one of those and see how they affect climate and whether they are matching up with the measurements that we see temperature-wise. So our first natural cause we'll look at is volcanic eruptions. When a volcano erupts, it is going to send large amounts of dust, gas, and ash up into the atmosphere. And depending on how large that volcano is and where it is globally, they'll depend on how much of the rest of the globe it impacts and how long-term those impacts are. So this is a picture of the eruption in Iceland in 2010, looking at it from Google Earth, seeing that volcanic ash go up into the atmosphere. This was not a large enough eruption to impact global climate. It was mostly just air travel disruption. So even that huge ash plume that we see there wasn't enough to impact climate. One volcanic eruption that was large enough to change global climate was by Mount Tambora in Indonesia in 1815. So when a large volcano erupts, it's going to send up large amounts of ash and particles from deep inside the earth, and a lot of those particles are going to contain sulfur, particularly as a gas, sulfur dioxide, and that gets pushed up into the troposphere, which is right next to the earth, and then even into the stratosphere if it's a very large volcano. So if we look at this timeline from The Economist of how a large volcanic eruption influences both distance-wise and time-wise areas after and around that volcano. So we get the eruption pushing all this gas, ash, and dust up into the atmosphere. A lot of those larger particles are going to rain out. And so ash is white, it's reflective. It is going to be reflecting any incoming sunlight. So let's say, we'll have our solar radiation coming in. That is getting reflected off of those ash particles back out into space. But most of those ash particles are going to rain down because they're relatively large. So within a couple days, that ash will have fallen out of our atmospheric layers. However, in the stratosphere, we are going to have maybe small, fine particulates of dust and sulfur dioxide. And so those little fine particulates are incredibly reflective of solar radiation. So any of that solar radiation that's coming in is going to be reflected out. And if this continues to happen for a long period, we can get global cooling because all of that incoming solar radiation that would normally balance out the heat of our planet isn't making it in. And so we get cooling over time because of that. With that particular eruption, we're not really sure how many people died. It's somewhere around 90,000 to maybe 100,000 people. And that was from the initial blast, so pyroclastic flow covering the area where people lived, from tsunamis that would result from that material going into the ocean and displacing ocean water, starvation from famine that would be caused by those changes in climate, as well as ash falling over all of the crops. Sometimes that ash includes toxic compounds like fluoride or things that will kill plants. So many immediate effects that happen, but there's also these long-term effects that happen afterward and in completely different places of the globe. So Indonesia, almost the entire other side of the planet, that ash that gets spewed into the atmosphere, it gets carried around by wind currents because of the Coriolis effect and because of differential warming, and ends up over Northeast America and Western Europe. And so in Northeast America, there was ground totally frozen all the way through summer. And if the ground is totally frozen through summer, and if you have days where it's snowing in the middle of summer, that's going to kill your plants, or your plants aren't going to grow. So there's widespread famine across the Northeast in that year. And so they called that the year without a summer. And there's literature, poems written about it, interesting imagery that's come out of that time period, where you would have no idea why that was happening, because maybe you don't understand those concepts yet, or you don't have the news that that volcano erupted last year. So it's just suddenly winter instead of summer. So another big cause of differences in global climate are oceanic cycles. We learned about thermohaline circulation a little bit, and we'll look at that again, but mostly we're going to focus on ensocycles. So here we can see our thermohaline circulation depicted as we get these moving warm surface currents that go up toward the pole, get pushed under as we get that freezing of the water as it goes toward the pole, expels all of its salt. That cold, salty water sinks, pushes the water underneath it, runs into all of these continents, and gets pushed around, runs into another continent, rises, warms again, and that continues our circulation. So that circulating water brings its energy with it. So cold water is relatively low energy, right? It can absorb more energy, store that energy as heat. So cold water that moves into a hot area, like the equator, like this current right here, moving cold water up around India, that's going to bring kind of relief from hot temperatures because it can absorb that excess heat. Whereas when we get this hot, relatively, water moving into colder areas, that's going to make winter and colder times less severe because we're bringing in energy that can be released from that water. So this kind of mediates global climate in mixing our temperatures. So the equator becomes less hot and the poles become less cold because we can distribute those temperatures around with our ocean climates, as well as our air climate, with our ocean currents as well as our air currents. Thermohaline circulation is this big global current system. We also have smaller cells sort of within that large system. And one of those is a oscillation that goes between South America, the west coast of South America, and Indonesia and Australia. So this area right here is where we get something called the El Nino Southern Oscillation, an ENSO cycle. And normally we have strong trade winds that are blowing from the east to the west. And that is due to the Coriolis effect and differential warming. So our natural cells that form over the planet and send air currents in different directions, one of those is sending strong air currents blowing from the east to the west. And that air pushes and pulls the water underneath it from the east to the west. So as we saw with upwelling, if you push that water off the coast, so the surface layers are going to be going from east to west, I guess video's backwards, so we'll go this way, then that is going to pull the water from underneath up. So all of this cool, deep water gets pulled upward as our surface waters get pulled over to Indonesia and Australia. And that's the normal situation. However, there are times where those trade winds slow down, so they're not blowing from east to west as strongly. And that slowing of those air currents, which is influenced by a lot of factors, will cause periods called El Nino. So times when the east to west trade winds are slowed and not as strong would be times where we are in an El Nino. On the top we have our normal situation, and then on the bottom it depicts our El Nino situation. So here you can see our trade winds are weak. So we have less of a strong air current blowing our surface waters. Now normally, because we have so much water being pushed toward Indonesia and Australia, you get this sort of bubble of warm water that's pressing all the cold water underneath it in this direction that then again helps push it up to the surface on that west coast of South America. Here that bubble expands outward because it's not being kind of forced this way, so it expands back towards South America. We get this current of warm water that then pools around this area that would normally have really cool water. So what this does is in Australia and Indonesia, it dries that area out because normally when you have all of this warm air and warm water, that's going to create a lot of precipitation. And so now that precipitation is either falling in South America over here, or it's falling in the middle of the ocean. So Australia and Indonesia get drought, and South America gets flooding. For us, these effects are pretty mild, but in that El Nino oscillation, those countries keep really good track. So if you wanted to learn about El Nino, you could look up information posted by the Australian government, because for them it can determine whether they're going to have a loss of all their crops that year or extreme weather events. So for us, for an El Nino year, which might happen every 3 to 7 years is kind of the average of that oscillation, it's predictable in that you can sort of keep track of surface temperatures and suggest that you're sort of moving into an El Nino or not, but it's not a set kind of time that it happens. So we get drier winters, slightly warmer, every 3 to 7 years when we're in that El Nino. For people who live in South America and Australia and Indonesia, it's much more severe. So you get flooding, severe storms, that'll change your fishing industry, and drought is going to affect your ability to grow crops. In addition to El Nino, you can also get the opposite. So in some of these periods, you get our trade winds becoming stronger. So that blowing from east to west is intensified, and more water gets pulled off the coast of South America. And so that just has the opposite effect, where your storms in Indonesia become more intense. So instead of having drought that you would have during El Nino, you get intense hurricanes forming. This is an infographic from the Australian government. If you go to this website, you can go further back in time by sliding this slide bar. I just took a picture of the screen. So this is showing periods that we had El Nino and La Nina. And you can see that it's not really very regular. Here we get several El Ninos in a row, right, where we maybe start to go sort of toward a La Nina, but then we're right back in El Nino. So that's an incredibly long El Nino period. And then you can have severe, shorter El Ninos, severe, shorter La Ninas, back-to-back La Ninas, long La Nina followed by a long El Nino. So it's different every year, and the effects of each of those El Ninos or La Ninas are different every year. So this is a regular cycle that is not predictable, but does influence global climate in somewhat predictable ways. Another natural cause of climate change are sunspot cycles. So a sunspot is a giant storm on the sun, and when that storm happens, you get eruptions of radiation from the sun that are then kind of spewed toward Earth, and that radiation contains energy. So anytime that there is a sunspot, that is extra radiation and energy that's going to head towards Earth, which can cause warming. So if we look at this graph of sunspot cycles, they tend to sort of peak every 11 years or so, where we get a lot of sunspots happening in those particular times. And those do cause warming on our planet. If we get these peak years of sunspots, we do see warmer temperatures on the Earth. And we can look at that. So here we get these peaks that are sort of corresponding with these global temperature peaks-ish. Maybe it's kind of dipping a little bit right there. But if you look at this lower graph of sunspot cycles, you can see they were getting less intense here around 2015. We still had a peak, but not as many as we had in maybe 2001 or 2002. But our temperature from then, oops, sorry, that's not a straight line, is still increasing. So this is not explaining this. It might explain this tiny little peak, but that's even a little bit offset, right? So we have a difference in our data here. It's not corresponding. We have a trend that isn't explained by these sunspot cycles. We can also look at other forms of data and see if those are matching our temperature trends better. This is dangerous, as always, because correlation is not causation. Just because two things do share the same trend doesn't mean that one causes the other. So you need multiple lines of evidence to support that, right? Also, when you build these graphs to convey data, you can change the way that the scales are set to make them line up perfectly with each other or not, as long as they're going the same direction. So always beware of how a graph can make data look. And so I don't think that you should look at this graph and be convinced that CO2 is the cause of temperature change, but after all of the information that we look at, I hope that you'll be at least a little bit swayed. So our fourth natural cause is a much longer term cycle. So Milankovitch cycles are these larger 100,000 year cycles that determine when ice ages happen on our planet. This is showing the mean global temperature over a very long period of time. So we're looking back 500,000 years here and seeing that every time we have one of these low points, this is an ice age. So this shows that our planet does go through these cycles. Before humans were having a large impact on the planet of extremely cold, quite warm, right? So we are oscillating naturally between these points. Some people would argue that we are just in a period where we're still increasing in temperature in this Milankovitch cycle. There are three major factors that are contributing to a Milankovitch cycle. The big one here is eccentricity. And so this is your real kind of 100,000 year period where the Earth's orbit around the sun will change from being very circular to being more elliptical. And that circular rotation means that throughout that whole year, we are equally close to the sun. And so that is less extreme sort of temperature shifts on our planet. As it becomes more eccentric, there are periods where we are more distant from the sun. We can get more extreme winters, and there's also periods where we're closer, right? So we can also get more extreme summers. So that has to do with how much ice will be forming and melting within those seasons. And so if we get periods where we have a lot of ice formation, and not a lot of ice melting, or maybe the ice is melting very rapidly but then freezing again, we have more period where we're away from the sun. Those are going to be periods where we would have ice ages. How we are tilted toward the sun also changes. So I gave you that figure of 23.5 degrees, but it can actually oscillate between 22 degrees and 25 degrees. And the more severe that tilt is, if it's closer to 25 degrees, that is going to be more extreme fluctuations in the winters and summers in our polar areas.